Hello, welcome to video 4 in our lecture Advanced Mathematic Modeling. In the last lecture I gave you a lot of rules how to calculate probability of events, independence of other events, and we showed also an example how to use this in practice. Today I want to introduce the conditional probability. That's the question. What is the probability of an event A if we already know that another event B happened already? We say the probability of A conditioned by B, and this bar here, this vertical bar, means the conditional probability. So how can we calculate this? And maybe I should say already that conditional probability, that's the point where our intuition, our common sense as humans often fails to calculate or to guess conditional probabilities quite often, and I will show you examples. Our intuition goes quite a different direction than what is the real number. So first, how can we calculate this? So let's do a Venn diagram. So here you see a Venn diagram. We have event A and we have event B, and we know that's the sample space omega, and we know the probability of A is the area of A divided by the area of the sample space. But now we know that B happened already, so B is certain. So this means the probability of A can only be these events which are in the intersection of A and B. The other outcomes of A are not possible because we know B is true. So we have the intersection, but this has to be taken relative to the size of B because we know B happened already. So the probability, that's the probability that we have A and B happened, divided by the probability of B. So that's the rule to calculate the conditional probability. And you can easily show this is really a probability, conditional probability, because it is bounded between 0 and 1. Now we can, with these conditional probabilities, we can do some nice things. Maybe the first is we can extend this to our rule for the intersection of probabilities. This was a bit disappointing, maybe, this rule, because this was not really a calculation rule, it was more a definition. We said the probability of the intersection is the product of probabilities if the events are independent. But what does this mean? But now we can, here we have also the intersection, so let's see what this gives. So first, if A and B are independent, then we know the probability of the intersection is the product of probabilities. Then we have that the conditional probability. Now for the denominator, this we can separate in the product of P of A times P of B, since they're independent, and so we can take here the product. We divide by the probability of B, and then you see we have just the probability of A. So if A and B are independent, the conditional probability equals the probability of the event. Now, but what's the case if A and B are not independent? But then we can just write this formula here a bit different. We see we find a rule for the probability of the intersection, probability of A and B. That's now the probability of the conditional. So that's the conditional probability times the probability of B. And so now we have also a rule to calculate probability of intersections, and this really complements this our 4 rules from the last video. Now we have something really real here to calculate the probability of an intersection. And now you could ask why did we here separate out B and not A? That's just definition. We could also have written this as probability, conditional probability B as a B conditioned on A times probability of A. That's just by symmetry. More interesting, it is more interesting if we look now for the intersection with the complementary event of B. That's an interesting application. Let's make this bigger so that we have here some space. So what is then the probability of A and the complementary event? And by this rule here, you can just write this is P of A conditioned on the complementary of B times the probability of BC. I mean, that's in the moment just we replace here B by the complementary event. But now something, we can now make a simple calculation. So what's the probability of A intersection with B plus the probability of A intersection with the complement? So now we can take the rule for the union. That's the probability of event A intersection with B, and then the union A intersection with the complement. Now, and if you look at this set, you see this is just the set A, so that's just the probability of A. And then you see the probability of A equals this sum of probabilities, and this leads to the important partitional rule. And we can write the probability of an arbitrary event A can be decomposed as the conditional probability A on B times the probability of B plus the conditional probability of A on the complement times the probability of the complement. That's a very cool rule in order to calculate probabilities, and we can even generalize this. So we have here, in the moment we used only B and the complement of B, but so we had just 2 sets, but we can generalize this to an arbitrary partition of our sample space. So what's happening if B1, B2 until n are a partition of omega. What do we mean with partition? So this means the union of all these sets is the whole sample space, but they all have zero intersections. Yeah? So just like B and B complement are a partition of omega, so you could have many sets which make a partition. And then we can write the probability of event A is the sum over all partitions. We have the conditional probability A conditioned on one of these sets multiplied by the probability of this event. Let me give you an example how to use these conditional probabilities and show you that your intuition sometimes can go wrong. So, an example. So, assume we have a family that has 2 children. We know one of the children is a boy, and we ask, what is the probability that both children are boys? And the assumption, of course, here is that the chance for a single child to be boy or girl is just 1/2. So how do we calculate this? First, common answer it says the chance that both children are boys should be 1/2. I mean, that's also, when I wouldn't think too much about this, that's also what I probably would say. We know one is a boy, and then what's the chance that both are boys here? So the second can either be a boy or a girl, so the chance is 1/2. But this is wrong. And here I would advise you, press the stop button in the video and try to figure out yourself what's the correct answer to this question. And when we want to do this, to get the correct answer, as I told you, try to make sure always what is the sample space and what are the events that we're looking for. So what is the sample space? That's the set, and this is defined by the event. We have 2 boys, we have a boy and a girl, we have a girl and a boy, and we have 2 girls. So we have a sample space of 4 elements. Now, what is our event A that we are interested? That's the set that we have 2 boys. And what is our set B, our event B? That what we know already. We know 1 is a boy, so B is defined as 1 child is a boy, because this is what we know, and this is the set that either we have a boy and a girl, or we have a girl and a boy, or we have 2 boys. And now we can use our rule for the conditional probability. So what we are looking for is the probability for the event A. So we have 2 boys given that 1 is a boy, given event B. And so this is the probability of the set boy boy intersection with the set boy girl girl boy 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 divided by the probability of B of the set boy girl girl boy boy boy. And now you see in this intersection yields only the set two boys, yeah? And here we still have this set here, boy girl girl boy boy boy, and here. So what's the probability of this? So this is now you could directly now either calculate. So this is set here as the size 1 and this has the size 3, or you can calculate what's the probability of this. This is 1/4. What's the probability of this? This is, because we have independent events, 1/4 plus 1/4 plus plus 1/4, and you will see we end up in total with 1/3. So the intuitive answer of many people, one of the two, would be wrong, and the correct answer is 1/3. And in order to build up your intuition with conditional probabilities, what you really have to do is to really construct these sets here. Okay, maybe we stop here and continue in the next video.